Hey guys, a little bit of a different video today. So I've got this Gen 3 LUDT. The previous LUDT buttons that I had made, which I actually have one of these down here, these are slightly different than the Gen 3. This is for a Gen 2 originally. And what I've been doing for the past, probably 75 or maybe 80 that I've made of these is hand grinding the lock face on here. The reason for that is the Gen 2 just used a cylindrical lock face, and there's kind of a tapered cone lock face on the Gen 3. So I can hand grind that in well enough, which is acceptable, and it works and it's reliable, but it's more effort for me. But the thing was, I've already got those in stock, or I've already got them paid for, I guess I should say. So since I've already got the money sunk into getting those made, the easier thing, or I guess the cheaper thing for me to do is take the 10, 15, 20 minutes it takes to grind everything into spec and do that by hand. So that's what I've been doing with it, and now I'm about sold through of that old inventory, and I need to reverse engineer what the new button looks like. Basically all I did when I received the Gen 3 LUDT in the first place was put one of the buttons that I had in, figure out, oh no, this doesn't work quite the way that I thought it would, and then I modified the Gen 2 button to fit, and then kind of made a blueprint for that for myself, so that way I knew, like, oh, okay, this is the size I need to grind it down to, and all of that. So there are some other details which I'll walk through, but I figure I'll show you guys kind of or I shouldn't say the process, but my process for reverse engineering parts, and just kind of talk through what we're doing and why we're doing it a certain way, and kind of what the whole deal is behind that. So it's gonna be mostly me talking. I'm gonna be taking this apart for a little while, and then it's gonna be me walking through how to take measurements with calipers and how to fully define parts to make sure you're getting exactly what you want. And that's kind of going to be the extent of it. So I guess, long story short, it's going to be a lot of me talking and explaining why I'm doing things a certain way. And it's not going to be so much of me talking about how to design a lock face or how to design a button. Because all we're doing here is we're reverse engineering an existing part, and we're not, like, I guess technically I'm trying to improve it because I'm putting the tritium inlays in there, but I'm not mechanically trying to improve it, right? I'm not trying to change up any lock geometry. I'm not trying to mess with any of that. All I'm doing here is trying to reverse engineer exactly what they've got, and copy it to, I won't say the most exact, but copy it as well as I can. So this is what the button looks like. You can see, hopefully it comes through, there's a little facet right here about halfway down. So, and you'll notice the difference on these previous ones that I made is it's cylindrical the whole way up, right? So what I would do is I'd grind this angle in, and what you do know is the size down here. So we'll take this and we'll measure it. So the largest diameter I've got there is 298, which I think should be exactly the same as the Gen 2 ones, 298.5. So within a half a thou, that's for all intents and purposes exactly the same, as far as lock geometry goes. But the difference here is you have this taper. So I'll try and measure this as well as I can. I think that's about as low as I'm going to be able to get. But you'll see that tapers down to about 290. So you've got like a 4 thou per side taper on there, on this specific one at least. And the fun thing, I guess fun, half annoying, is that with these LUDTs, and probably with a lot of the Microtechs in general, there's the different size stop pins, and then I think these buttons also come in various sizes, and I forget where that's indicated. I think on some of them it's indicated as like dots on the bottom, or it might be little grooves in the side or grooves on the bottom here or something, right? But there's some indicator on this button somewhere, or at least historically there was, that tells you exactly what size this is going to be. So for this one, we're going to reverse engineer exactly this. When I get them made, I'll get them made to this size, because this seems to be the largest that I found, is that 290 thou on the top. And then all I need to do is grind it down, 2 thou per side or something like that, just to get it into final spec, if I even have to do that in the first place. So I guess we'll talk about a little bit of reverse engineering here. You need a bunch of dimensions for this, right? So the way that things like this are typically modeled is about a center line. So when you model round parts, typically it's good practice to like cut the part into a section. And what we're looking at here is going to be the center line. So this is like right down the middle axis right here. So if you could imagine, if I rotate this guy around, it's all symmetrical around a circle, right? So if I take this and draw it, we have the top of the button here, and then you can see there's a little chamfer coming down. So this little angle doohickey guy is coming down like that. And then this comes down, and then we've got a little relief groove in the bottom like that. And the purpose for that, I guess everything else is pretty straightforward. The purpose for that relief groove is that way you're never interfering with this little groove that's cut in the bottom of the scale there. Because anytime you're turning parts, right, your lathe needs to come in, and your lathe has, even if it's really small, some sort of radius tool like that. So you need to be able to come in and cut all of this, and you'll never get a 90-degree corner here with a lathe. You can get really close, right? You can get really, really tight radius tools. But the easiest way to make sure that you have clearance at this little flange joint right here is to actually come in a little deeper around the bottom. So that's kind of the easy way. There are harder ways to get a true 90 degree or very close to a true 90 degree, but that's going to be fine for now. So now that I've way overdrawn that, that'll be fine. But then we're going to come over here, and then we have our stem that comes down. So this is kind of the middle section of the button right here. And then this guy comes out, and then we have this chamfer that comes down like that. This guy comes down straight here, and then the button comes over flat. There's actually an internal hole for the spring, right? So this is gonna come over something like this. It's gonna come up internally to some dimension, and then it's gonna come straight back across. And now hopefully, if you see where I'm going with this, I can sketch all of this, right? And then I can tell my computer program to revolve all of this around here, and then I've got a full solid object. And then I can come in and I can cut a circle for the tritium in the top, and I can cut a slot in from this direction here. But this is kind of your building blocks, right? So in order to make these parts, or in order to fully define these parts, we've got to come up with all of these measurements. And the easy way to picture it is right now is nothing's defined, right? So if I was in my computer program, I could click on this line and I could drag it side to side, and I could drag it up and down. So what we want to do is fully define everything so that all of it is rigid and defined, and that there's nowhere that any lines can go if I pick them up, right? So I guess the easiest place to start is your overall height, right? So I have 420 thousandths, which nice. So we're coming over here, and we'll say that this to here. So we're gonna make a little hidden line there, dimension line, and this is gonna be 0.420. So that's gonna come up here, and that's gonna come down here. So as far as your constraints go, now what's gonna happen is if I was to click this line and drag it up and down, it's gonna drag this bottom line up and down with it. And a lot of the other stuff is gonna change, but at least that is fully defined. So we've got that. Next thing that we can do is measure a bunch of the diameters, right? We'll get to a bunch of the lengths in a minute, but I wanna knock out some of these diameters because they're all fairly straightforward, right? So 2975, 2975. So we measured this at 298 earlier. There might have been some dust or dirt or something to make sure that this is zeroing out. Good. So we're zeroed out there, which is good. There's no dust, no debris, no nothing. So 297.5. I'm gonna call it 298 because what I don't want to do is make this too small because I can't add material back on after it's subtracted, right? So what I can do is I'm gonna come over here, draw this guy, and I'm going to say the diameter is 0.298. So we've got that. Good there. The taper we're going to get to in a minute because that's a little bit more complex, but that'll be fine for now. We want to measure internally here. Now this isn't the best tool for measuring internal holes. Since this is just a clearance hole for a spring, I'm not overly worried about it. So 203 is going to be fine, right? Like if we measure the outside diameter of this spring, these are all going to be roughly the same. And this is what we need to fit in there, and that's 193. So if we go up to 203 there, we've got 10 thou clearance diameter in there, that's going to be completely fine, even with some spring tolerance and everything. And even if we make this hole a little undersized, it's still going to be completely acceptable. So we are going to call that the 193 that we measured. 193. So that's good. And then we can do the depth of this hole now, because that is easy enough. So this is a fine tool to measure for that. Again, there's better ones that we could use. And then we've got 99 thou. So we'll push that up to 100 thou. And if it looks like a thin wall in the model, we can figure that out when we get to it. But we'll put it as 100 for now. So we got this guy and 100 thou. So we've got that there. So now I'll pause a little bit. I'll talk through this. If I was to drag this guy up and down, all I'm gonna do effectively is push this whole thing as a unit now, because this is defined and this length is defined. So all we're gonna do is push this, and this other stuff is gonna stay still for now, but the other stuff is gonna move around. So you can see bit by bit, we're fully defining this, or we will be fully defining. This diameter, we're not gonna be able to move at all, right? If I try and pick this up and drag it, I can't, because I'm defining this diameter and I'm defining this. Chamfer here, we can still mess with. I'm gonna get to that in a little bit. For now, we're gonna do this like thin stem that's in the middle. So you can see we're at 184 here. So again, we're gonna come over here like that, diameter, 0.184. So we've got that. Next, we got our flange on the outside, so 329. Now this one, some of these I've been upsizing, some I've been downsizing. This flange, we definitely don't want to be over 329, because there is a chance, it's a small chance, but there's a chance that this is the absolute biggest that a button ever comes. Now the issue is, if I make this at any bigger than this size, that 298, or 298, 329 that I've got here, there's a chance that it interferes when someone puts it in their knife. So if I make these and they come out at 331, which is still pretty close, but they could not fit in someone's knife, and that would be an issue that I don't want to have to deal with, because then I got to go glue up a new one, I got to send them a new one. So 329 is going to be the max there, and I have to take that into consideration when I'm making the actual blueprints. So for right now, we're going to write, what was it, 328, something like that, 329. So we're going to write 329. But when I make the blueprints, this is going to be a maximum, right? So I want it to be lower than that, because all this needs to do is prevent the button from shooting out through the knife. So that's all we want to make sure we're doing with that. And that, you know, that's the whole function behind it, the flange right there. So we just want to make sure that that's big enough to do its job. And if it's a little undersized, that's okay. But we definitely don't want it to be oversized. Now this guy is about 300. So we'll set 300 as the max for this, because I don't want that to be too big. So we've got this here is 0.300. Now I've dropped off the diameter symbol in a couple places, so I'll add that on there. But chamfer wise, this is kind of a design feature, right? There's nothing crazy that needs to happen with a chamfer. You'll notice my older ones, I don't even really have any significant chamfer on here. There's a little edge break, so it's not a sharp edge. But otherwise, it's really not a necessary feature. And my goal is to make these with the highest viewing, or the longest viewing window that I can. The chamfer kind of interrupts that. So maybe I'll add one in there, maybe I won't. So this will be one of those things that I potentially add in later, but it won't be this big in all likelihood. It'll be a little bit smaller. Not super critical, and we'll do that once I start getting into the nitty gritty. But next detail I want to do is come over here, and I want to measure this height. So we've got this, and then height-wise, you want to take your calipers like this is the easiest way. And because I got this nice convenient flange there, I can measure it like that. Now you've got 117. What I like to do for stuff like this is just do it a couple times, because some of these measurements can be a little finicky to take, especially if you're just doing it with calipers. It's really not exactly the right tool for this, but you know, it's what I've got. I'm gonna work with what I've got, and that'll be good enough. So we're in between 116 and 117, and this height isn't super critical. It's got to be tall enough that you can press the button, but it doesn't need to be like dead nuts every single time. The button can get pressed a little lower, a little higher, you know, whatever the case ends up being. Now we're gonna want the flange thickness here in the bottom. So we've got his 18 thou, so that's perfectly fine. Got that there. And then I've kind of drawn myself into a corner here, but the right way to do this would technically be not like this, but it's what we're gonna do. So we got that, and we're gonna cross over, and it was what, 18,018. Good, and then we need this height here, alrighty. So that's 154 roughly. So that's gonna be this guy. $154. All right. And then that's basically everything, right? We've got all our diameters for all the critical features all the way down. The only thing I don't have a diameter for is the top of this taper. And the only thing I don't have a height for is the height of this taper. So those are the two things that I need, is the height of that taper so that I can establish whatever the geometry of the lock face is. And then I need the diameter, the smallest diameter that I can measure of the top of this taper. So those are the only other two things that I need. Everything else I've got, right? I've got all my diameters, all my heights, all my everything. So everything is good from that perspective. Now, the easiest way to do this is gonna be by eye. You know, there's definitely other ways that you can do this, probably a little bit cleaner, but we'll be able to get pretty close for this. And we're just gonna look through here and see if we can line everything up pretty well. And I'm seeing like 65 thou, which if we look at this, you can use your dimensions as reference. We have 100 thou total, or excuse me, it's not 100 thou total height. This whole guy is 130 thou. And if you look at it, it looks like roughly half, right? So we'd probably look in the 65 thou range, somewhere around there, which is really like pretty dead on to what we're looking at. So we're gonna call it 63 thou for this height. And that's something that I can't really change as far as the height goes. I mean, I can, but it's gonna mess with the angle a little bit. And since this button, I'm fairly confident, just based off experience and other ones that I've measured, fairly confident this is the largest size button that they offer. What I can do when I receive these, if I have it ground to 63 or have it cut to 63 here, I can always take off a little more material, right? So instead of it being this angle, it'll still be the same angle, and it'll just come down a little bit further, and that'll be fine too. And we'll just be taking off a very little bit amount of material from right here in this like shaded area. So that material will be going away, and it'll be a little bit smaller. So in the case that you need your button to extend a little bit more, or your blade is drilled a little bit smaller, this kind of button will be able to work if you grind this face, or I guess if I grind this face. So most of these that I send out, I try and do in the middle ground, and if it ends up not working, typically it's because it's too large, and I'm able to grind a new one, send that out, and everything ends up working fine. So this is probably the most finicky part of measuring these tapered buttons, is getting the smallest diameter. So you remember earlier I measured this at 290. We're just gonna try and walk this up as much as I can, and hope for the best, you know? And whatever the smallest measurement that I get is gonna be the smallest measurement that I get, and that's what we're gonna go with. So I think 290 is about as small. I know it said 289 there for a second, but it can be a little tough to get this kind of dead nuts on here. And I like to use the square jaws of the caliper for this instead of the pointy ones. I find it helps hold a little bit better. But I think we're gonna call this 290. And I'll set that as my minimum that I want it at. So it could be a little bit bigger than that, but the smallest I want the top of this is 290. So now effectively, we have all of the points that we need to model this. And you'll remember I mentioned earlier that sharp corners aren't completely possible. These radii here, it can be really whatever. You're never really experiencing those radiuses as far as use goes. Your blade's never gonna be touching that. So functionally, they don't need to be sharp corners. External sharp corners are completely fine, and then this guy is fine too. So you can see there's a little center drill mark there for when they plunge a drill bit, or I guess just a drill into into this hole, remove some material. And this is the only one where you really need that undercut. So I will keep this in there just in case it's doing anything special. But everything else, there's going to be a standard nominal radius in there. So I'll put 0.015 here and here, and then this, I'll just give them whatever freedom, right? So instead of flat bottomed hole, sometimes it's easier if you make this like a drilled hole. So you can imagine, like, if you pick up a drill bit out of a drill index for drilling holes in sheetrock or whatever, they're all kind of shaped with the cone shape on the end, and there's standard drill angles for that. And I think the typical countersink is 120 degrees, maybe 137 degrees, something like that. So that might not work for this, but they could remove the bulk of the material with that kind of drill, and that's going to get you a hole like this, and then they'll just come in and clean this up on the inside. So you'll still have a little bit of a mark there, which you can kind of see, but that's not a functional thing. That's just an ease of manufacturing thing, and it's not causing any issues. And then after I model all this, so it'll be swept, or it'll be revolved around this axis, we're going to go in and model in my viewing slot on the top and the installation hole on the side, and those are going to be just two other things. So largely it'll look exactly the same as this guy, but there will be minor differences between the two. Mostly you can see there's a height difference, which is I'm pretty sure to accommodate not the blade stock thickness, but the fact that it's on bearings now. I think they've just added basically one bearing height to the stem here, so that way there's a little more freedom for the blade to open. It works perfectly fine on these, right? I've had dozens of these installed on knives and never really any issues. They just sit a little bit lower, but this allows the button to stick out a little bit further. And most people like the button to stick out like the factory one does. It can be kind of alarming if you install one of these. One of the buttons that I've made for the Gen 2s in a Gen 3, and it's ground to work, and it'll work in that knife, but it's now much lower profile. So you've got to press down a lot further into the recess in that top scale. So you're really kind of getting in there to press it, which is a little bit safer, but it's you want to maintain uniformity from part to part if you can. So when they swap it out, it's as close as possible. It's just got the tritium vial in there, and hopefully nice finishing. Everything looks good, and fairly close to factory in that aspect. It's just got the vial in there is the only difference. So as far as reverse engineering parts, that's kind of the whole thing. This is one of the easier parts, which is why I figured I'll walk through it on this, and I had to do it anyway. But if you guys want to see other parts reverse engineered within reason, I'm not going to show you how to do scales and everything, because it's a much more complex process and much more involved, and the measurements take a lot longer. If you got a 3D scanner, something like that is perfect for stuff like this, where you can scan the whole thing, turn it into a model, and then you can take a couple hard dimensions, so you can measure the width and the length and all of that stuff, and then you can scale the model appropriately and make tweaks however you need to. So that can be a really good tool. And whether you send that out to someone to get it to get it scanned so that you can reverse engineer it, or if you do it yourself, a lot of phones these days can do the reverse scanning, or you can buy one for couple $100 to a couple $1,000 if it's something that you see yourself turning into a business. I know a lot of these guys that make carbon fiber scales have to reverse engineer scales all the time, right? So some of these guys have the tools to reverse engineer, which a really beneficial thing for that might be a 3D scanner. So that's kind of the whole process. There's not really much more to it than that. So if you guys want to see any other specific reverse engineering like processes or questions, or how you do it, or how do you determine what's important versus not important, a lot of it is just being around stuff and seeing how stuff works and seeing how it's put together. But if you got questions about it, you can leave me a comment, and there's a chance I'm able to help. I don't have experience reverse engineering absolutely everything, but I have done a fair amount of reverse engineering in my day, so you can always ask, and the worst I can say is, hey, I haven't actually done that kind of part, so I can't really help you with there. And that may be the answer, maybe it won't be, but yeah, I guess if you have any questions, please leave a comment or a question, or shoot me a message, or however you want to do it, and we will try and figure it out from there. But yeah, I mean, the buttons really are pretty straightforward, at least the round ones. Apparently installing this guy isn't so straightforward though. There we go. That was annoying. Yeah, so I mean the buttons, especially with like the tapered lock faces, really aren't anything crazy to reverse engineer. It's pretty straightforward. There's nothing like ridiculous about them, as long as it's done reasonably, right? I'm sure that there's some companies out there that are making some absolutely wild buttons. Any of the Microtech stuff is typically pretty straightforward. It's all they're designed for manufacturing. I'll say is pretty good. Some of the stuff can make the manufacturing a little bit more difficult, but none of it's ever like completely obscene. At least from stuff that I've seen. So it's come on, this thing killing me. There we go. Yeah, they do a pretty good job with it for the most part. And like, there's gonna be things that you need to watch out for with some companies versus other companies, right? Maybe some company is doing all of their tolerance adjustment in their button, right? So now you really need to have people send in their knife if you're trying to do retrofit buttons or modifications or whatever, because all that tolerance is in the button, and there's 10, 50, and 20, 30 thou of difference between every button. But companies like Microtech, it's like they do have a couple different sizes as far as I can tell. There's at least 3 different sizes of buttons. There might be more. So what I'll typically do, like I said, is shoot for the middle ground with it. If there's issues, there's issues, and I figure that out when it happens. Typically the customers are really quick to reach out, especially when they've paid for something. You pay good money for a button expecting it to work. When you go to put it in your knife and it doesn't work, that's an issue. Unfortunately, there's no, like, as far as I can tell, no readily available way to figure out exactly what a button size is. And not everybody has a pair of calipers sitting on their desk at home. So it's not exactly like I can ask every single person that wants one of these buttons, hey buddy, can you send me these 3 critical dimensions, and then have them know exactly how to measure each individual thing. I mean, it's just not really a reasonable thing to expect out of people. So shooting for the middle ground or shooting for the low ground is typically the easiest way that I've found to do it. And that tends to work fairly well. I've had sometimes, especially on some of the Microtechs that are on like the way wrong end. Like I had one, you saw that we measured this guy at 290, right? So typically, for reference, I will grind most of the ones that I sell, to like the 286 to 287 thou range on the top at the smallest I can measure. Very occasionally I'll go a little bit smaller than that, but almost never bigger, because that tends to be pretty reliable. And kind of your worst case scenario when I grind them like that is your button sticks up a little bit further, and it's very slight because it's a pretty aggressive chamfer. So this here is a pretty aggressive angle. So it sticks up a little bit higher, but typically like imperceptible. But there was one that I sent out, and the guy said, hey, this isn't even close. And his button, I think I had to grind down to like 278 thou. So if you think about tolerances, a lathe is going to be able to hold the 0.001. So instead of 290, this will be 289 or whatever. This thing was like 50 in thousandths smaller under this button, which you look at percentage-wise, that's almost 5%. So this button was 5% smaller than the standard button that I send out, which is bananas. That's a huge tolerance variation. And when he sent me pictures of the button, the thing was all like jacked up and jammed up, and it looked like they had like hand ground this thing to fit in the first place. So it made me feel a little bit better, because Microtech had to like hand grind and hand fit a special button to fit this knife. And instead of throwing it in like the blemish bin and calling it a day on that, they actually send it out to this customer as a typical knife, like a standard knife. So that's just like a little piece of reference, right? For like, sometimes there's going to be things that go wrong, even when you reverse engineer parts perfectly and you figure out the tolerances. I'd say the only other thing in addition that you'll want to look at is it's usually worth buying like 3, 4, 5 different parts to try and reverse engineer. And ideally, you want them to be from different batches, right? So Microtech, at least, I can't speak to other manufacturers, kind of makes everything all at once, right? So what you'll want to do is you'll want to buy one, and this one has the production date, call it, June 2025. Maybe you want to wait another couple months and get a completely different model, right? So this is DLC. Maybe the DLC comes back from DLC a couple months later. So this is actually potentially the same lot of machined buttons as something that was like 2 months earlier. So if you want to buy like a standard finished after that, maybe you buy a standard finish and then you reverse engineer that one and you see, okay, we're about the same, we're a little bigger here, a little smaller here, whatever. So you can kind of build your tolerances and figure it out from there if you're going to manufacture things in the first place. So at this point, I'm kind of rambling. This is all the dimensions I needed. So I'm going to go ahead and model this. We're going to assign tolerance bands to it, make blueprints, get these made, and these will be in 440C this time. So the old ones were in 17.4 pH, which 17-4 pH is a fantastic steel. You can harden it to like 43 to 44 Rockwell, but 440C, you can get up to like, I don't know what the max hardness is, but you can definitely get this up to like 60 Rockwell. So what that's going to do, it's not going to wear down as quick. It's going to last a little bit longer. Microtech's using the M390MK on all their blades, which I'll make sure that I heat treat these softer than that, so that way I'm not wearing down the blade. But the button will last longer is the intent, right? Once we grind this lock face in, it's going to stay there, and it's not going to grind. It's not going to go away, because what happens, you have your blade steel banging into this time after time after time. And if you have a big hardness differential, like this 43, 44 versus a 62, 63 Rockwell hardness blade, you can cause deformation. And now their factory buttons, I'm fairly certain, are 17.4, but I think this 440C is going to do better. And we'll be able to harden these just in kind of a typical way to get it up to this 60. And I think it'll resist wear a lot better, and it'll functionally be a lot better too. It's going to suck a lot more to grind, but that's going to be my problem to deal with. And we're removing a lot less material. Before I was removing 4 thou per side. Now at most I'm going to have to do like 2.5 or 3 thou per side. So I'm removing a lot less, and should be a lot more straightforward, because when I machine these, this angle's already going to be there. So it's really easy for me to index against that face and take off some more. So that's that. If you guys have any questions, material selection, reverse engineering parts, how to take measurements, etc., please let me know. I'm happy to help where I can. And thank you very much for watching, and have a good one.